We'll start the session now. And good afternoon, everyone, and welcome back for the second day session. We are conducting a workshop on next generation automatic modeling and simulation with AMS software. So these are like 6 sessions with 1 day Q&A session, and we are on second day session, that is today. And today's session is about two photon absorption using AMS software by Dr. Franco. And in this particular presentation, we will be introducing TPA spectroscopy, its uses, and the underlying theory and present ways to simulate it using the AMS software. So with the specific examples. And before I introduce the speaker to everyone, I would like to just show the last day's slides and recorded details where I've uploaded. And I've already emailed all the details last day to all the registrants. Just let me share my screen where I've uploaded the slides. And I hope everyone can see my screen. So this is the Google Drive where I've shared the link to everyone last day. And I've also shared the download links for the software. You can download and install the software trial license, and it will be valid until October 15th. And if you have any issues in installing the software, you're always free to get back to me, write an email, or you can just call back to the number which is given in email. So these are the slides, and I will be uploading every day after the session, day 1, day 2, day 3, accordingly. And this is the day 1 session that was last days. And in this text format, the resources I've mentioned the recorded session and as well as the tutorials, workshop exercise, everything. And regarding yesterday's recorded session, we have uploaded in YouTube. I'm just showing the link. YouTube. So this was yesterday's session. And the third one is we have uploaded yesterday's slides, which was taken by Dr. Ole. You can go through all the slides. And if you have any queries, please do get back to us. And there are tutorials also on the ReaxFF software. On the same link, it will be updated every day as accordingly day 1, day 2, so that you can like click on the same folder link. So you will get updated links every day post session. So I would like to welcome Dr. Franco for the session. Thank you so much for joining us.
Yeah,
And I
thank
would
you,
like
Dr. Suman.
Thank you. So I would like to introduce Dr. Franco to everyone. So he is a software developer for the SCM, and he joined SCM in the year of 2021. So Dr. Franco earned PhD in chemistry at SNS, Italy, on modeling of electric properties and Raman spectra of molecules in solutions. He worked as a postdoc at University of Washington on two-component relativistic effects before returning to SNS as a researcher, and he was involved in the implementation the QMFQ polarizable force field model in Amsterdam modeling suite. So over to you, Dr. Franco. You may share your screen.
Okay. Let me see. Entire screen. Okay. Does that work for you now? Can you see my screen?
Yes.
Okay. Thank you very much for the introduction, and thank you for organizing this event. So today I would like to talk about two-photon absorption spectroscopy. Okay. Yeah, so this is a spectroscopic technique to analyze a chemical system that is a little more exotic compared to regular one-photon absorption or fluorescence spectroscopy, but it is quite powerful, and I hope I will show you why in this brief presentation. So today,
Dr. Franco, I'm sorry to interrupt. Can you make your screen full? Slides?
Yes, okay. Can you see a full slide now?
Actually, no.
Okay, I'm gonna try something different then.
Sure.
Let's see. Okay, can you see now my full screen?
Yes, perfect. Thank you.
Perfect. Okay, so I'm glad that works now. Okay, so just a brief summary of what we're going to talk about. I'm going to give you some background on this technique, on the photon absorption spectroscopy. I'm going to give you some just general background as well as some theory. I'm going to talk about how we calculate the spectroscopy using the AMS software. And then I'm going to give you two examples, two very different examples on ways to use the software to simulate this type of spectroscopy. So let's start with the background. So two-photon absorption spectroscopy involves the simultaneous absorption of two photons by a molecule. So if you look at the picture on the right, you can see that in this case, we have two photons of frequency omega, which are absorbed at the same time, and they cause the system to jump from the ground state to an excited state. And the difference in energy between the two states is equal to 2 omega. So the two photons together cover the entire energy difference between the two states. Now, though in general, the two photons do not need to have the same energy as long as the sum of the two energies corresponds to the energy difference between the two states. So you could have omega 1 and omega 2, which are different, but if the sum omega 1 plus omega 2 is equal to the energy difference, that still also is classified as two-photon absorption. However, the case when the two photons are have the exact same C frequency is by far the most common, because then you only need one light source to perform the experiment. So that's why it's much more common. So because it involves two photons at the same time, TPA is a non-linear process, which has a number of consequences, which I'm going to talk about. One of them is that the cross sections for this spectroscopy, that is the intensity that you get, is usually very, very small. It's much smaller than one photon absorption, which is a linear process. And so one has to take care of certain problems in order to use it fully. And another thing is that it obeys very different selection rules compared to one photon absorption. So some states which may be not visible with your one photon absorption experiment could be visible in two photon absorption, because the transition is no longer forbidden. For a little further on the what you can do and what you can study. So on the picture on the right, you can see some molecules which are known to have higher than average two photon absorption spectroscopy cross section. And I wanted to show you this to give you more of a concrete feel of what the phenomenon is about. So why is it high in this case? It is high because these are very highly conjugated molecules where you can have a very large charge flow within the molecules. You have these charge transfer states, which are excited using the two-photon absorption. And another reason two-photon absorption is important for these molecules is because they involve transitions between states which are highly symmetric and have the same symmetry. So some of you may know that in regular absorption spectroscopy, if two states are symmetric and have the same symmetry, typically that transition is forbidden. So it's not visible in the spectrum. But in two-photon absorption, that's not true. It is, in fact, visible. So for example, let's take molecule number 3, the one in the top right. So this is a highly conjugated molecule, and at the two ends of the molecule, you have groups, chemical groups, which are electron donating. You have these nitrogen atoms, which have non-bonding electrons, which can be donated to the rings and flow throughout the molecule. So when you have a transition from the ground state to the excited state, that's what happens. These electrons are excited and they go into the ring. So you have a charge transfer that goes from the two ends towards the center of the molecule. Because these two states have the same symmetry, this transition cannot be induced with just one photon. You need two photons. And this is why, for this molecule, this is an important spectroscopy. You can also have the same thing, but instead of donating electrons, you have the groups that take electrons out of the molecule, like in molecule, for example, let's see number 7, where you have these cyanide groups, which are electron attracting. So for the transition, in this case, you have electrons moving from the center towards the ends of the molecule. But nevertheless, it's still a symmetric transition. So the two-photon cross-section is higher, and whereas the one photon is forbidden, so it's very low. So this is just an example to give you a feel of what it's like chemically. But in order to simulate this phenomenon, we need to know what to calculate, of course. But first, I would like to point out that, like I said before, two-photon absorption is very weak generally because it is nonlinear. And when you have a nonlinear spectroscopy, like TPA or even Raman, which is much more common, but it's also nonlinear, you need a strong source. So when like a regular lamp is often not enough. So usually you need lasers. You can use lasers to just like in Raman for two-photon absorption. But the thing with lasers is that they're expensive often, especially if you want tunable lasers, because of course your molecule can have its transition with any type of energy. You don't know what energy that's going to be. When you buy a laser, though, usually the laser works with one frequency or just the harmonics of that frequency. And there are tunable lasers, they exist, but they're very expensive, and you need very expensive optical equipment as well to work with those. So that can be tricky. But there is another possibility, which is taking advantage of plasmon enhancement, or also known as surface enhancement. This happens when you take your molecule and you place it on top of metal nanoparticle, for example. You then shine your laser light onto the metal nanoparticle, and the plasmon resonances that are induced on the metal nanoparticle give you 1,000-fold or even more enhancement of the field acting on the molecule. And this enhancement causes the two-photon absorption. This is a very common phenomenon used in a lot of different nonlinear absorption, nonlinear spectroscopies, including Raman for SERS, and also TPA, like I'm going to show you. So you have these two different possibilities to perform the experiment. And of course, because we are the computational chemists, we want to be able to calculate both, obviously, to simulate. So from the point of view, or theoretical point of view, the fundamental quantity that one needs to calculate to simulate the spectrum is the second hyperpolarizability. So in the equation at the top, to the left, you see this is the equation for the sigma, that is the cross-section, that the intensity of your two-photon absorption. That is a prefactor with a bunch of numbers. Then you can see we have to take the imaginary part of the sum of gammas. So these gammas are the second hyperpolarizabilities of your molecule. And the second hyperpolarizability is simply a term in the Taylor expansion of the induced dipole. So when your laser or your light reaches the molecule, because it is an oscillating light, it induces an oscillating dipole. on your molecule. And this oscillating value dipole depends on the electric field that is applied on your molecule. And if you expand it in the Taylor series, you have a few terms. The first term is the standard polarizability, and that gives you the one photon absorption, so not regular absorption. If you go to the gamma, that's where you get your hyperpolarizability, your two photon absorption. So this gamma is a very complicated object. It is complex, so you have a real and imaginary part, but for TPA, we only need the imaginary part. And it has 4 indices, each of which can be x, y, or z. So you have 3 to the 4th terms, which we can calculate in general. And you can see in the equation at the top which terms we will need to build the sigma TPA. So this calculation involves the calculation of the response functions of your molecule, the dynamic response functions, typically damped response functions, because you will need both real and imaginary part. Of course, the program in our case does everything for us, so we need not worry about it directly. We can just, I will show you how to use the program to achieve this and get your results. We can calculate TPA from the damped response functions in ADF, the Amsterdam density function. That's the QM engine that you can find in AMS. And the method takes advantage of the known 2n+1 rule for density derivatives, just as to say that the calculation is not too expensive because it doesn't involve the calculation of second derivatives or third derivatives of the density. These are just some details. We use the IO response module that takes care of the calculation. And so far I've only talked about the molecule itself. Of course, if we want to do a meta nanoparticle, that is way too big to calculate using quantum mechanics. So we use a different model called the discrete interaction model, which I'm not going to go into detail about today because we want to focus on TPA, but we have lots of information about it and I can answer some more questions. But this is a semi-classic, it's a classical model which treats the atoms of the meta nanoparticle classically, and it is a polarizable electrostatic model. So that means these atoms can be polarized and they can induce the plasmons, which will cause the TPA transition. I'm going to show you 2 examples. First, we are going to see how to use, very simply, the graphical user interface to calculate the TPA of para-nitroanilin, this molecule on the left, just regularly in vacuum. Then I'm going to show you a different way to use our software, completely different way. Instead of using the graphical user interface, I'm going to show you how to do scripting with the software by using Python. We can use Python to access the software. I think my colleague Ole talked about this yesterday as well. And that allows you to really fine-tune your calculation and do all sorts of things that you can imagine if you are capable of doing some Python scripting. And I'm going to use that to do the calculation for this system. So the para-nitroanilin, as before, but we're going to show you how to place that between 2 meta nanoparticles to create this nano junction, which then induces a really high field enhancement. Okay, this is it for my presentation, and I'm going to jump right in to the demonstration. I hope you can still see my screen. So I'm going to show you, what I'm showing you right now is the graphical user interface. Once you open the program, this is what you see. On the left, we have a panel where you can draw and create your molecule. And on the right, there are lots of options for selecting whatever calculation you want. So let's say I want to calculate para-nitroanilin and the 2 photon absorption. So the first thing I need to do is to draw and create my molecule. Now, you have a panel here where you can select different atoms and you can start drawing your molecule. But in our GUI, graphical user interface, we have a faster method, which for simple molecule gives you a library with pre-created molecules. So I'm just going to write p-nitroanilin here, and you can see that I get different options based on my query. And the first one is indeed the para-nitroaniline that is being optimized with ADF. So I'm going to click, and there it is. I have my molecule drawn right there. This has been pre-optimized with ADF. Of course, if I change the parameters of my calculation, I may need to do an additional geometry optimization. But I'm not going to do that now because I want to focus on TPA. So I have my molecule, and now I need to select my model. So if I want to do a DFT calculation, first thing to do is to select the exchange correlation functional. So I go to the right, and in this menu, I can see different types of functional described in here. Default is LDA, but it's not very good. Obviously, it's the most basic thing that you can do. Well, of course, we have GGA functionals, hybrid functionals, or even certain models, like, for example, SAOP, which is one that I'm going to use today. After choosing your DFT functional, you can choose your basis set. I'm going to select, for example, TZP, a triple zeta basis set, which is very good for these calculations. And I can select the frozen core level. For example, I'm going to do all electron calculation by selecting none. And this is for the quantum mechanical model. But now I need to tell the program that I want to do TPA. So I go to the top and select properties. And here you have a list of properties that you can calculate using ADF. You can see there's all sorts of properties. If you want to do gradients, geometric gradients or infrared spectroscopy, Raman, or even things like one photon absorption, UV visible spectroscopy, GW, all sorts of things. There is a very long list. But in my case, I just go to hyperpolarizability because, as I've said before, this is the property that gives you TPA. So I select here. By default, this is not calculated, so this is none in this case. And you can see if I hover on the menu, it gives you a list with an explanation of each property and what it means. But I can just click and go down the list to find the gamma TPA, which is the property that we want. Once I select this gamma, you can see that more options light up, because for two-photon absorption, I want to select the frequency of the laser. So if you're using, for example, an experiment with a laser, you need to tell the program what the energy of this laser is. And this is by default specified in electron volt, but I can also change the units over here. Let's say I want a laser in 1.71 electron volt. In this way, the program will calculate the sigma, so the cross-section for TPA for that frequency. And you can also add more frequencies if you want to this list. And that's it. So I have, if I run this calculation, this is what the program is going to do. It's going to calculate the gamma and all of the gamma components that I need for this frequency. And to run the program is very simple. You can just go here and select run from the menu. Once you select run, the program will prompt you to save, of course, your input, and then it will run the program on your computer. It does take a while. This calculation, I think it took me 45 minutes, so I'm not going to do it in real time, but I do have the results already. So once you run the calculation, this window opens up with your calculation, which I call vacuo, because it's simply the isolated molecule. It shows you the local file, and it shows you the calculation in real time, which you can follow. You can also look, once the calculation is finished, you can look at the output by going to SCM output. You select output, and you open the output file, which I was already also opened, and you can see the results over here. So this is the output file of your calculation. It is a large file because it includes all of the results. It includes the energy, it includes the bond analysis, the charges, everything about your molecule that has been calculated. You can navigate it using the menu at the top. For example, I can go to section results, and it will show you all of the results of the calculation. Or you can navigate it with this toggle on the right. But here I've already gone to the bottom of the calculation, obviously, where I can find this section called TPA second hyperpolarizability. And this is exactly what we needed. So these are the frequencies that you see specified in the gamma here. So this is, they're all the same because it's omega-1 is just one frequency. So this is the frequency that I have specified in the input. It looks different because this is in atomic units in Hartree, whereas I had inputted the frequency in electron volts initially. But nevertheless, this is my tensor. You can see second hyperpolarizability tensor. These are all of the components of the tensor, and this is exactly what you need. And you can use these components to build whatever quantity that you need. And in this case, you can just go back to the presentation, and you saw what the formula was to assemble the sigma. So you would have to take these numbers and assemble them into the sigma that corresponds to TPA. So you can see, even though this is a very complicated spectroscopy, running the calculation is actually quite simple. You can just do everything using the graphical user interface. But this is the simplest case, of course. Suppose you want to do something more complicated, like, for example, the surface and the plasmon-enhanced version of this, where you have the molecule with the metal nanoparticles. Doing that is also possible using the graphical user interface. You just need to load. Typically, it's difficult to create a very large metal nanoparticle atom by atom by yourself. So usually one creates it in a file and then loads the file into the graphical user interface. So it is possible, but I don't want to show you quite how to do that because it would be the same as we've just seen. And I'd rather show you how to do it using Python scripting, which is completely equivalent. So you can do the same things with the Python or with the graphical user interface. But for a lot of people, using Python is much easier and versatile because you can do everything in there, including the results analysis. So we have, on our website a tutorial which goes step by step on how to do this. So for more information, I invite you to go there, and you can find all of the information and the explanation, and it should be very easy to follow. But here I'm just going to show you the main things involved in this procedure. So I have opened the Python script in Visual Studio, so you can see what it means. So this is a simple Python script, which I also you can find all of this also. You can download it from our website, along with all of the structures, so you can reproduce this by yourself. And you can see the first thing that you do is import the packages that you need. You don't need a lot of packages. The most important is, of course, scm.plums. Plums is the Python library that we have and we ship with the software that allows you to use our software. You then initialize your calculation, and you define the things that you need. For example, we have the geometry file of paranitroaniline. You have a geometry file of one of the meta nanoparticles and a parameter for the meta nanoparticle itself. We have a bunch of constants, and then we create our molecule. We have very simple functions to use. Like, for example, the molecule function just loads the geometry file into a molecule object. And we can do the same thing with the meta nanoparticle, create a new molecule object for the meta nanoparticle, which then gets translated in order to not overlap with the molecule. And you can create a copy and rotate it and shift it. This is because we want to create this. We want to create one molecule at the center with two meta nanoparticles identical, one on each side. And you can sum the two regions. So the dim region, so that is the meta nanoparticles, is just the sum of the two. You then define your settings object, which contains things like the DFT functional and the basis set, and all of the options. You then specify the omegas in electron volt, that is the frequencies. So it's the same one that I selected in the graphical user interface. This is 1.71 electron volts. you can define some parameters for your calculation. So you can define all of the parameters using this Python scripting technique. But of course, all of these also have defaults. You define some parameters for the DimQM. I'm not going to show you exactly what each of these mean, because there are more information on the website. It would be a bit tedious to go over each and every one of them here right now. This is just to give you an overview of what you can do. So this just creates the input file. And then over here, we have a for loop, which runs over the frequencies. Of course, you can specify more frequencies, because if you want just one frequency, you get one cross-section. But if you want an entire spectrum, you need to run the calculation several times for the different frequencies. And here, this Python script runs two jobs, so one after the other. One for just the molecule, and one for the molecule with the nanoparticles included. You can see the power of the Python scripting here. So instead of having to redraw everything and do it separately, which is what you would do using the graphical user interface, here it is very simple to do it in a for loop if you have some experience with Python. You define your job object, you run the job here. It's very simple. You can see you just do job.run, and then you extract the results. So this is an NumPy array, which is created by parsing the output and going and grabbing the numbers that I showed you before from the output, from the gamma. And because this is a Python script, of course, it's very easy also to create the sigma. So on this line, you can see sigma TPA is simply the formula that I showed you before in the presentation. So you have the sum of the gamma imaginary parts with the indices that were in the formula. The exact same thing is also done for the molecule in between the two metal nanoparticles, and the sigma is created. After one does that, you can just print the results. And this is the entire script. You can see this is a quite complicated calculation, but the script itself is actually not very long. If you remove the comments, that's less than 100 lines of code for running two separate calculations, even for many frequencies. You can run this script on command line or Visual Studio using your favorite interpreter, and this just generates as output the different frequencies. And so these are the two ways that you can run our software. Almost basically every type of calculation that our software can run can be done both with the graphical user interface or using this Python scripting technique, as well as other ways, such as writing the input directly from command line, if you like to do that. And that's it. This is a very simple way to run your calculation, and I hope you're gonna try yourself if you like. And if you have any questions, of course, I'm here to answer them.
Hi everyone. If you have any questions, you can post it in Q&A tab, or you can unmute yourself and ask the question.
I see a question in the chat, which functional should I use? It really depends on your molecule. So for organic molecules, for example, there are standard functionals like p3lip or pp0 are very good, or PBE, for example. If you have more complicated molecules like transition meta complexes, you need to refer to the literature to see which functionals are appropriate. It really depends on the system.
Hi, Franco. There is a question in Q&A tab. Shall I read for you?
Yes, please.
Okay. So for a non-scripting person, how the scripts could be easily used in AMS? I understand the PY script is provided by SCM.
Yeah, so the script that I just showed you, you can be downloaded from our website. So you don't have to write it from scratch. In fact, we have lots and lots of examples and tutorials where you find the script that was pre-written. So you could just run it. And of course, changing a couple of parameters in a script is much easier than running from scratch, than creating one from scratch. But of course, if you really don't want to script, it's entirely possible to just use the graphical user interface. I could import coordinates and import the coordinates of the meta nanoparticles into the graphical user interface. I think you can still see it, right? So in this case, I have imported the coordinates into the graphical user interface without scripting. And of course, because of the way they were defined, they overlap with my molecule. So I want to move my molecule away. So I can click on one of the atoms, select molecule. This way, I can grab the molecule and move it around independently. And there you go. So now I have the molecule on top of the meta nanoparticle. And I can run the calculation on this system. Of course, in order to do what I did before, so use the quantum mechanics on the molecule and the classical, the polarizable classical force field for the meta nanoparticle, I have to define the two regions. And you can do all of this from the graphical user interface, no need for scripting. And we have tutorials on how to do that on the website.
Any more questions from the participants?
I can see what would be the frozen core and numerical quality. Frozen core can be used with any DFT functional, but in my case, because I chose this model SIOP, you need to do all electron file calculation. But of course, I can select PVE and do small frozen core or normal. That's fine. Because TPA is usually a balance type of spectroscopy, you don't need, you may not need frozen core. It just depends what you're doing. And the numerical quality can also be adjusted. Is there any possibility of using multiple basis set? I'm not sure I understand. So you can use, of course, one basis set for a geometry, for example. You can do a geometry optimization using a triple zeta p basis set. And then you can do the TPA calculation using a different basis set. Maybe if you have readbacks, if your excited state is very diffuse, you may want to add some more diffuse functions, for example. And we have a long list of basis set that you can choose over here. You can see if you can add, for example, diffuse basis functions like this. It really depends on the type of electronic excited state that you want. But yes, it is possible to use one basis set for the geometry and one basis set for a different one for the TPA. Yeah, different basis set for different molecules. Yes, of course. Each time you do a calculation, you can select a different basis set. Ah, no, you mean for different molecules in the same calculation. You can specify basis sets atom by atom. It's a bit more complicated, but almost everything is possible. Sometimes that's necessary, indeed.
Any more questions? You may unmute yourself if you want to ask.
How can you use it for studying to intermolecular forces? So this is a completely different type of calculation. Of course, it's possible to do that type of calculation depending on the size of your system. But for that, I invite you to look at our examples. We have a few examples that show how to calculate interaction energies. I can see a question: how to run the calculation for tautomeric structure? You may have to draw different structures. So if you have two tautomers, you just draw them separately and run the two calculations separately, and you get your bonding energies for both. So that way you can calculate the energy difference between the two, if that's what you are interested in.
Hi, Franco. There is one more question in Q&A tab. What are the plotting capabilities in the AMS package?
We do have plotting capabilities in this tool, AMS Spectra. So in this case, I only calculated one frequency. So there is very little to plot, obviously. But if you calculate a spectrum, for example, many excited state when you do one photon absorption, or many frequencies, even for TPA, you can open this tool and you can draw the spectra. So I don't have a calculation right now to show you. Of course, you can draw your spectrum directly from the output. You can adjust your axis. You can analyze each transition. You can draw the orbitals, and you can print the spectrum. So we have a special tool just for this.
Any more questions?
Hello, sir. Good afternoon. Yeah. So my question is, if a molecule has a tautometric structure,
Yes.
So in one calculation, how can we get the tautomeric structure calculations? Means, is there any hydrogen? One more thing, I would like to ask you that, how can we draw the hydrogen bond in the AMS input? And that thing, if it is forming a hydrogen bond tautomeric structure, so how can we run the calculations?
If you have a molecule which has different tautomeric structures, maybe you, if I'm understanding, so if you want to identify whether or not there are tautomeric structures, we have a tool for finding isomers in general, any type of conformers, sorry. So that will give you the conformers, but then you would need to move the hydrogen yourself. And if you have an intramolecular hydrogen bond, and you can see it in the molecule, that is automatically calculated. So I'm not sure that answers your question. So if you have two completely distinct tautomers, then you have to draw them separately and do two calculations.
Sir, how can we draw the hydrogen bond in the AMS output?
So if you have a hydrogen bond in your molecule, or even if you have two separate molecules which have a hydrogen bond between them, we have a few bonding analysis techniques that you can do based on others, the atomic molecules. You have quite a few bonding analysis techniques that are applied. So maybe some of them you need to ask from the input. Others are always calculated by default. So if I go to my calculation for TPA, to the results section, you can see lots of different results. So electron density at the nuclei, the Mulliken populations. This is all automatically calculated. The Hirschfeld charges, Voronoi charges, multipoles, and you can calculate and analyze bonds using special techniques. So these are all the MOs, for example. So if you want to study a specific bond, you can ask for bond analysis in your calculation. I hope that answers your question. I can see also another question in the chat about the computational cost of this work. So this calculation for the two-photon absorption of the molecule alone, you can see. So I started this. This was on 32 cores. I started this at this I think took about 50 minutes. Oh no, there it is. This is the final CPU time, system time. So it's very fast, this calculation. And also, the version with the metal nanoparticles is not more expensive. It's almost the same cost because the DIM method does not add a lot of computational cost for the calculation. Now, of course, I ran this calculation on our cluster. So this is it's a powerful computational cluster with where I have access to machines with 32 cores. But I could run very well this calculation on my workstation, which has 8 cores. I have done it before. So for molecules that are this size, like paranitroaniline, even on a laptop, you could probably run. Of course, if you want to run a very large molecule, then you may need higher performance. Typically, you don't need more than like 32 cores is already extremely good. I wouldn't go more than that, and you don't need a lot of RAM to run these types of calculation. For QM calculations, RAM is not needed unless you do post-Hartree-Fock. So you don't need a lot of that either. So of course, the faster is your CPU, the faster is the calculation.
Any more questions?
I think there is one. Oh. What is the running time? I can show you the running time for this calculation. So I ran this yesterday, you can see. So the calculation started at 18 hours, basically. So at 6 p.m. and it ended at 6:04 p.m. So this is the running time of this computational work. So you can see this was very fast. This is the log file, by the way. So I just opened it using right-click. If you right-click on your calculation, you can open the output, the log file, the spectra, if you have spectra. So here, this is the log file which logs all of the major steps of the calculation. And also tells you the time at the exact hour when each step was finished. So you can see. So this was very fast. But then again, I did run on 32 processors in this case. You can see 2 nodes, 32 processors up here. Any more questions? I don't see any on the chat.
Yeah, Franco. In that case, like if there's no questions, you can stop sharing the screen. I will just present my screen to conclude the session.
Okay.
Thank you so much. I hope the screen is visible. So tomorrow also there is a session and it will be at 5 o'clock and that will be taken by Mr. Srijit Soman. And rest of the 5 sessions will be at 5 o'clock only. Well, I would like to conclude the session for the day and thank you everyone for joining for the session and special thanks to Dr. Franco. Thank you for your time and for the wonderful session. So we will wind up the session for the day and see you all in the meeting tomorrow at 5 o'clock. Thank you so much.